Alright, welcome to Physics 1, Lab 1, Constant Velocity. So, the purpose of this lab will be to observe the motion of a rolling object that is moving with constant velocity, and we're going to observe similar motion of an object moving with constant velocity simulated by a computer model. We're also going to compare observations about the two different aspects of this experiment, so compare the two models together. So, some key assumptions for this experiment is that there is no resistance of any kind. There is no friction, there is no air resistance, there are no other forces acting upon the object, and that the object will move in a continuous straight line along the x-axis on a flat surface. So, some important principles to understand before we get into the actual experiment data. So, Newton's first law of motion. An object at rest remains at rest, and an object in motion remains in motion at constant speed and in a straight line unless acted upon by an outside force. So this is what's going to happen in our experiment to the can. We're going to move it slightly before the beginning of the video, and it's going to continue to move with a constant speed and constant motion in the same direction. We can see this here, the position update formula. So you have a given position, you're going to move it, the velocity times the time, and it's going to update the position. Newton's second law of motion. The net force on a body is equal to the body's acceleration multiplied by the mass of the body. So for this, we're looking at the momentum update formula, which is the same as velocity. So you have some given velocity, and you add to it the force times the time divided by the mass of the object, and that's going to change the speed of the object that much. Experimental methods. So for the real life experiment, we're going to track it using a software called Tracker. The system will be a monster can, the surroundings will be a ruler used for scale, and a lab bench. The forces acting on the system that will be observed are the push provided slightly prior to the recording of the data, and the forces not observed will be friction, gravity, and air resistance. For the computer model, which will be generated with GlowScript, we're going to have a system of a ball. The surroundings will be everything else within the simulation, which is nothing. And forces acting on the system will be the initial velocity and nothing else because there are no other forces in the data simulation. Tracker inputs. So Tracker uses supplied video to help track frame by frame the position and velocity of an object. So as you can see here in this video, we have our red little diamonds, and those are the position data points that you pick for the center of mass of the object in the video, and you can see them here as the time goes along. Frame by frame, you get the X position that you marked frame by frame. You can see here it tracks it for you. It'll give you the X position with respect to time, so the slope of this is the velocity. We also have a frame of reference. In this case, it's a ruler. It's used to scale the video. It's along this blue line. It's kind of hard to see because it's behind the can, but it's 6 inches, and we transfer that to meters because Tracker uses meters. GlowScript inputs. So at t equals 0, the X position according to Tracker data was 0.01813 meters, and at t equals 0.017, the first timestamp in Tracker, the X position was 0.01364 meters. So using these numbers, we can calculate the initial velocity of the can by dividing the change in position by the change in time. We find that the initial velocity of the can was 0.331 meters per second. For this experiment, the velocity in the model will be constant, so the net force will be 0. The video is recorded at a frame rate of 60 frames per second, so the delta t will be set to 160. Then because there is no net force acting on the ball, the velocity will not change and the mass of the can will not matter. So we can see all these things in the code right here. We have the system mass, we have the initial position, we have the initial velocity 0.331, we have the time, we're starting the time at 0, which makes sense, and then the delta t is going to be the frame rate, which is 1/60. We have while the video is going, so we only recorded about 1.3 seconds of motion, and we have the net force, and we calculated that to be, we're setting that to 0 for this experiment because we're assuming no other forces. And then you can see the rest of it, the momentum change, the time change, and the plotting of the positions. So for the results, we can see the graph of the model. The model has a constant velocity, and so it actually moves constantly along this line. The graph of the Tracker, it shows almost constant, but not quite. And so when we compare these two graphs, we can see that the Tracker, the real-life object, actually moves a little bit more over the given time period than the model predicted it to be. So the result of the experiment was that the can did not roll at a constant velocity. This could be due to a number of errors having anything to do with possible tilt to the table, possible air pushing the can, or some other force not considered by the experiment. If the can had moved slower than the model, it's possible that this could have been due to friction, a similar but opposite tilt to the table, or some other force. Other errors could have been due to rounding, placing of the center of the mass in the Tracker, or some other error in calculation or data entry. Further questions. What if the axis and the tracker were flipped? None of the numbers would actually change. The slope wouldn't change. It would just become either negative or positive. Or if you used the y variable instead of the x variable, it would roll vertically instead of horizontally. But nothing would actually change. Was the net force 0? Because the model assumes the net force 0 and the model and the experiment were slightly different, there was clearly not an actual net force of 0, and instead there was some other forces acting on it. Is it possible to see how many forces are being added together to give a rough force of net 0? No, it's not, because when we tried to add the forces together, we should have gotten 0, but we didn't get 0. So there must have been forces that were unaccounted for in the experiment. Thank you for watching.